make different circuits, we have to use several capacitors, and these several capacitors may be connected mainly in two ways, and that connection of several capacitances are called combination of capacitances. And there are two types of combinations. One is called series combination and another is called parallel combination. As we have earlier studied, this is for resistance. We have already studied series combination of resistances and parallel combination of resistances. Now we are going to discuss the series combination of capacitances and parallel combination of capacitances. Of course, there will be also mixed combinations, that is combinations of series and parallel combinations, that is called mixed combinations. And the effective capacitance of the two combinations, series and parallel combination, we are going to find that. Effective capacitance is that in place of a combination of capacitors, if we put a single capacitor with the same result, then that capacitance of that single capacitor is called effective capacitance of the combination of the capacitances. Now first we discuss about the series combination of capacitor or capacitor in series. Let us take three capacitances, three capacitors of capacitances C1, C2 and C3, and made a series combination. Series combination is like that. The first plate of capacitors 1 with capacitance C1 is connected to the voltage source, that is connected to the source of the charge, and the second plate is not grounded, it is connected to the first plate of the second capacitor. Second plate of the second capacitor is not grounded, it is connected to the first plate of the third capacitor, and the third capacitor may be connected, the second plate of the third capacitor may be connected to the fourth, and so on. And the last plate, that is second plate of the last capacitor, is grounded. Right? This is the series combination with capacitance C1, C2 and C3. C1, C2 and C3. Now if the charge given to the first capacitor plus, then it will induce minus Q charge on the inner side of the second plate of capacitor C1, and the outer side, that is on the rear side, will be charged by plus Q, and that will be on the first plate of C2 capacitor, and this charge will induce minus Q charge on the inner side of the second plate of the second capacitor, and plus Q charge will be induced on the first plate of the third capacitor, and this charge will induce minus Q charge on the inner side of the third capacitor and plus Q charge on the outer side of the third capacitor, and that will go to the ground like this. Now let us say the potential difference across capacitance C1 is V1, across capacitor C2 is V2, across capacitor C3 is V3. See here, each capacitor possesses same charge Q, right, with different potential. Now we can say Q equals to C1 into V1, and for the second capacitor we can say Q equals to C2 V2, and for the third capacitor we can say Q equals to C3 V3. Now from here we can say V1 equals to Q by C1, From here we can write V2 equals to Qyc2, and from here we can write V3 equals to Qyc3, and the total potential difference V equals to V1 plus V2 plus V3. Total potential, there is potential difference between the first plate of the capacitor C1 to the second plate of the capacitor C3 is V will be equal to V1 plus V2 plus V3. Now you replace these three capacitors by a single capacitor of capacitance C with the same result. That means the potential difference between the two plates is V as of the combination, and charge on each plate is Q. Same result. Then for this case, we can say Q is equal to Cv or V equals to Qyc, and this C is called the effective capacitance of C1, C2 and C3. Now put here V equals to Qyc, V1 equals to Qyc1, V2 equals to Qyc2, and V3 equals to Qyc3 or Qyc. Q may be taken as common and bring it outside the bracket. Then we can write Q into in bracket 1 by C1 plus 1 by C2 plus 1 by C3. Now Q cancels out. We can write 1 by C equals to 1 by C1 plus 1 by C2 plus 1 by C3. Now we can write 1 by C is greater than 1 by C1. Is it? 1 by C is greater than 1 by C1. Or we may write C is less than C1. Similarly, we can write 1 by C is greater than 1 by C2. Therefore, C will be less than C2. That means effective capacitance of series combination will be less than the smallest capacitance, right? Or small will be smaller than each capacitances connected with the series combination. This is one thing. Again, second thing we can calculate or we can get from here that if all capacitors have the same capacitances, then we can write 1 by C is equal to 1 by C1 plus 1 by C1 plus 1 by C1 plus dot dot dot. If we connect n number of capacitances, n number of capacitor with same capacitance C1 in series, then we can write the effective capacitance C like this: 1 by C is equal to 1 by C1 plus 1 by C1 plus 1 by C1 plus dot dot dot, that is n number. Or from here we can write 1 by C equals to n by C1, that is C is equal to C1 by n. If we connect n number of capacitor with same capacitances, then effective capacitance will be 1 by n times of a single capacitor. It's parallel combination of capacitors. In this case, also we take the three capacitors of capacitance C1 and C2 and C3. It is connected like that. The left plate of each capacitor, is connected to a common point, and right plate of the three capacitors also connected to a common point, and right plate of each capacitor is grounded. Let us say capacitance of this capacitor is C1, this C2 and this C3, and put this point to a voltage source. Since this point is common to all the three capacitances, and this point is common. That means the second plate or right plate of each capacitor is connected to a common point, and also the first plate, that is the conducting plate, is also connected to a common point. Then in this case the potential difference across the two plates of each capacitor will be same, and that is taken as V. The potential difference across the two plates of each capacitor will be same. Now if from the voltage source Q charge is given, then this Q charge will be divided into three capacitors. Let us say Q1 will be the charge on capacitor C1, Q2 will be the charge on capacitor C2, and Q3 will be the charge on the capacitor C3. Then we can write Q1 is equal to C1 V1, V1 is V, Q2 is equal to C2 V, and Q3 is equal to C3 V. Now if we replace the combination of three capacitors by a single capacitor of capacitance C, of charge Q, and with the potential difference across the two plates is V. That is same potential difference as of the combination, same charge as of the combination. Then this capacitor is called effective capacitor of these three capacitors, or this capacitance C is called effective capacitance of C1, C2 and C3. And in this case you can write Q is equal to C into V. And already we have told that Q is divided into Q1, Q2, Q3. That means Q is equal to Q1 plus Q2 plus Q3. Now put Q is equal to CV, and Q1 is equal to C1V, Q2 is equal to C2V, and Q3 is equal to C3 into V, or CV equals to, and V is common here, therefore in bracket C1 plus C2 plus C3, V cancels out, or you can write C is equal to C1 plus C2 plus C3. This is the effective capacitance C is equal to C1 plus C2 plus C3. That is, effective capacitance will be sum of each capacitances in case of parallel combination. And this is C here is also from here you can say that C is greater than C1, C is greater than C2, C is greater than C3 also. That means effective capacitance is greater than the each capacitor or each capacitances. If we connect n number of capacitances, then what happens? Then the effective capacitance will be equal to C1 plus C2 plus C3 dot dot n number. And if each capacitor have the same capacitances of C1, then C will be equal to C1 plus C1 plus C1 dot dot. That means C is equal to L into C1. That means in this the effective capacitance of a combination of parallel combination of n number of capacitor with same capacitance C1 is equal to N into C1, that is n times of each capacitor. This is for parallel combination. For series combination, charge will be same for each capacitor, but for parallel combination charge is not same, right? And the second thing is voltage is same or potential difference is same across each capacitor for parallel combination, but not for the series combination. These two things you have to remember. First thing, for series combination you have to take that charge on each capacitor is same, and potential difference, total potential difference will be equal to sum of the potential differences of each capacitor. And for parallel combination, you have to take or you have to remember that the potential difference across each capacitor is same, but total charge will be equal to sum of the charges on each capacitor. To calculate the effective capacitance, you have to remember these two things. And for effective capacitances, you have to remember that for series combination, reciprocal of effective capacitance is equal to sum of the reciprocal of each capacitances. And for parallel combination, you have to remember that effective capacitance of parallel combination is equal to the sum of each capacitances. These are all from series and parallel combination. In circuits or in numericals, you get both in the same circuit, series and parallel, and that is called the mixed combination. And for that case, you have to consider when parallel combination, you have to write this result, you have to take this result, and when there is series combination, you have to take that result. That means 1 by C is equal to 1 by C1 plus 1 by C2 plus 1 by C3, etc.